Bismillah ar-Rahman ar-Rahim. We are going to solve some problems related to electric field and electric field due to point charges. And we start with this example here. Example 1. It says we have 2 point charges, Q1 and Q2 are separated by a distance of 12 centimeters. At what distance from charge Q1 is the net electric field due to the 2 other charges? At what distance from charge Q1 is the net electric field due to the 2 charges? 0. Okay. So let's draw. Here you need to draw. So example number 1. Okay. Example 1. Electric field due to point charges. So I have 2 charges, and both of them are positive. So I have plus Q1, and then I have another charge here, plus Q2. This is 1 microcoulomb, and this is 2 microcoulomb, and they are separated by a distance of 12 centimeters. So I take this as my x-axis. If I take this as my origin, this will be 12 centimeters here. Of course, in the problem, it didn't mention where it is going to be this point. So it cannot be, this point cannot be outside this x-axis, okay? Because if you take any point here, for example, you can see that this charge is going to create an electric field in this direction, and this charge, which is positive, is going to create an electric field in this direction. This will be E1, and this will be E2, and both of them, they never cancel, because they will cancel probably along the x-axis, but not along the y-axis. As you can see, they can never cancel. The only location will be along the x-axis. Now, along the x-axis, you have 3 possibilities, because you have 3 regions. You have region 1 here on the left. Let me just do my x-axis like this. So you have region 1 here on the left. So region 1, region 2 between the charges, and region 3. Okay, so we have to test all these 3 regions and see which one will give us the possibility of having the net electric field equal to 0. So if we go to this point here, which is on the left in region 1, on the left of Q1, you can see that if we draw the vectors, the 2 vectors, because the electric field is a vector, Q1 is positive, so its electric field will be in this direction. Okay. And Q2 is also positive, its electric field will be also in this direction, radially outward, okay? So this is E2. So E1 plus E2 will never be equal to 0, because you add them here. You see, you have to add them. Let's go to region number 3 here and do the same thing. Let's take a point here, an arbitrary point here, and see. Of course, to have the electric field equal to 0, the net, they should be opposite direction, the 2 electric field, to cancel each other. But here they cannot cancel here. You can see them, because for a positive charge, the electric field will be outward. For the positive charge, the electric field will be outward. And both of them are to the left, and therefore they can never cancel. If you go to this side here, let's try this side. You can see the positive charge Q1 will have an electric field in this direction, E1, and Q2 will have an electric field in this direction, E2. Okay. Also here, they cannot, E1 plus E2 can never be 0. Okay, can never be 0. So the only location will be between the charges. Okay. So let's take a position here. I call this one X, because he wants at what distance from the charge Q1. This is the charge Q1, so I want this distance here X. Okay. So let's draw now the 2 vectors E1 and E2. So the positive charge here will have an electric field in this direction. I call it E1. And the positive charge here will have an electric field in this direction. I call it E2. And you can see clearly that both of them are in opposite direction. So if the magnitude are the same, then they cancel each other. And the net electric field due to the 2 charges will be 0, because they cancel each other. Okay. So let's write that E1 in magnitude should be equal to E2 in magnitude, so that when you add them vectorially, they will be equal to 0. Okay. So what is the magnitude of E1? E1 will be K, these are point charges, K Q1 over the distance between the charge and the point, which is x squared, equal the same thing here, K, which is the Coulomb constant, Q2 over the distance, this distance here, which is 12 minus x squared. This distance here is 12 minus this distance, it will be 12 minus x squared, okay? So K and K will cancel. Q1 is 1 microcoulomb, so I put 1 over x squared. And Q2 is 2 microcoulomb, I put here 2. Of course, 10 to the power minus 6 here, and 10 to the power minus 6 will cancel over 12 minus x, the whole thing squared, okay? So I'm solving for x, I'm looking for the location or the distance from the charge Q1, I'm looking for this x here. So I have x squared, so I have 2x squared equal 12 minus x, everything is squared. The best thing to do is take the square root from both sides. So we have x square root of 2 equal plus or minus 12 minus x. Okay, so you have two solutions here. Let's look at the positive solution, okay? Positive solution, positive here, plus, the plus sign there. So we'll have x square root of 2 equal 12 minus x. So I will have x, 1 plus square root of 2, I bring this to this side and make the common factor x equal 12. And x in this case will be 12 over 1 plus square root of 2. If you do the calculation correctly, you should get 4.97 centimeter. 4.97 centimeter, which is almost equal to 5 centimeters. So the distance is almost equal to 5 centimeters from the Q1 charge, okay? The other solution, the negative solution, negative here, the negative sign, if you take the negative sign, of course it will not give you the correct solution because the point will be outside. And mathematically, okay? Then you have to use the physical solution, which is correct, which is the point will be inside, okay? Will be inside between the charges. So this will give you the wrong answer. This will give you the wrong answer because it will be more than 12 centimeters, which means outside, and therefore physically it's not correct, okay? Now, so this is how you would solve this problem. The final answer will be 5 centimeters from the charge Q1, okay? Now, if you want to, so the 5, so if this is 5 centimeters, okay, this distance will be 7, okay? 7 centimeters. You notice that the point is closer to the charge, which is smaller in magnitude because of the distance squared here. As the distance, if you want to equate the two numbers, the charge is higher than this, so this distance should be smaller than this, okay? And you can see it, 5 is here and 7 is here. Now, if I, for example, the problem is finished, if you want to elaborate more, you can have a positive charge Q1 here and a negative charge Q2 here, okay? And this is 10 microcoulomb, for example, and this is minus 20 microcoulomb. You will see later, if you do it correctly at home, this is just, I'm just giving you a hint here, how to solve these other problems. Here the two charges are equal. By the way, if the two charges were both of them negative, the answer will be the same. But if one of them is positive and the other one is negative, the electric field, the net electric field, which will be 0 on the outside, okay, not in between the charges, it will be outside the charges, and it will be closer to the charge which is smaller in magnitude. So my point will be here, okay. This is a point where the electric field E net will be equal to 0, and I call this distance x, and you solve in the same way, okay. You solve in the same way. So these kind of problems, if you see that you encounter this kind of problem, if the two charges are either positive or negative, both of them the same sign, the point where the electric field will be 0 will be between the charges. If one of them is positive and the other one is negative, the point will be outside the charges, and it will be closer to the smaller charge in magnitude, okay. All right, thank you. Okay, let's look at now example number 2 related to electric field due to point charges. Of course, the first example was a one-dimensional problem. So we were working in one dimension along the x-axis. Now we go to a two-dimensional problem here. You can see it says two identical charges, each of charge Q, are positioned at point A which is 5, 0, and point B, which is minus 5, 0, to produce a net electric field equal to minus 10J unit vector, and at point C, which is at 0 and 5. So this is a two-dimensional problem. So the first thing you have to do is to draw your axis so that you can locate the positions of these points and charges, okay? So I have a charge, I have a positive charge here. They're identical. They don't say are they positive? The most important thing is they are identical. They are either positive or negative, okay? We will see if they are positive or negative. We will see, okay? So I take my charge Q. This is 1, 2, 3, 4, 5 here. This is point A. And I have a charge here, Q, okay? All right? And then minus 5. 1, 2, 3, 4, 5 with a minus. I have another charge here, okay? A charge here, which is a Q again, the same magnitude, okay? A charge Q. I'm going to put the sign later by looking at the electric field. Now, at this point here, 1, 2, 3, okay? 1, 2, 3, 4, 5. At this point, point C, I have an electric field pointing in the negative Y direction. So let me draw that electric field there. Of course, you should know that there are two electric fields actually. So this is my electric field here. There are two electric fields at this point. And these two electric fields are due to the charges, and they are like this, okay? The figure is not drawn. Let me draw it correctly, okay, here. Okay, let me draw it correctly here, okay? So my points are 1, 2, 3, 4, and 5, okay? So I have a charge Q. So let me now draw the line joining the point charge and the point C. See the point C, this point C here, okay? Now, you can see that if the charges were positive, okay, the electric field will be in these directions, and the net electric field will be pointing in the positive Y, okay? So we can directly tell that these charges are negative, okay? They are both of them negative charges. And therefore, the electric field due to each one of them will have this direction. This is E, I call it E1. Charge number 1, charge number 2, okay? And this will be E2 here, okay? And I'm sure these two electric fields, they have the same magnitude, okay? And of course, this in red, this is the net electric field, okay? That's the net of the two charges. Now, why is it in that direction? Let me tell you why. Of course, you take your axis here, okay, and then you decompose these two electric fields. E1 will have a component along the x-axis, and you'll have a component along the y-axis. This is E1. E2 will have also a component along the x-axis and another component along the y-axis. And you notice that these two components along the x-axis, they are opposite in direction, they cancel each other. Okay? So you have a net electric field pointing in the negative y direction, minus 10J. So this is the magnitude of the electric field, and this is its direction along the negative y. So this is how you can tell about your charge. So the charge is negative here. If the charges were both of them positive, my net field will be pointing up because the electric field will be going out radially outward here, E1 and E2, and the net will be pointing upward. Now let's now do some calculations to find the charge Q, the value of the charge Q. Of course, this value here, 10, is affected by the value of Q. If the number is different here, the value of Q will be different. For which value of Q? Give me an electric field of magnitude 10 Newton per Coulomb. Okay, so because this is a square, this is this here 5, and this is 5 centimeters. You can see, okay. You can tell that this angle here is actually 45 degrees. 45 degrees. That's the angle. I need that angle, okay. And I need this distance here between the charge and the point, which is square root of 50, right? Square root of 50. That's 25 plus 25 square root of that is 50. It gives you 50, okay? That's the distance between the point charge and the point charge and the point where the electric field is given to you, okay? And also this distance here will be the same thing. square root of 50 because the charges are equal in magnitude. They are at the same distance from the point. Okay? Now, let's calculate E net. So, E net along the x-axis is 0. I hope you know why. Because these two vectors, the blue components, they cancel each other because they are equal in magnitude and opposite direction, because the charges are the same, the distances are the same, so the two cancel each other. I'm left with Ey pointing downward. So Ey net, which is given by this value here, the 10, is actually equal to, I have to put a factor of 2, because I have two components, and both of them are in the same direction, y direction, 2k q over r squared. I'm going to write r squared now for now, times the cosine, this is the cosine of 45. Cosine of 45. But when you have 45 degrees, you don't have to worry too much because the sine and the cosine are the same. Square root of 2 over 2, so you don't have to worry about that for now, okay? Now, so this should be equal to how much? This net, the 2 is for the two components. Each one will contribute the same. So 2kq over r squared, the distance squared, times the cosine of the angle, which give you this component, y component. And this should be equal to what? It will be equal to 10. The magnitude of this vector here, okay? That's 10 there. You can put here equal to 10. So 2 times 9 10 to the power 9, that's Coulomb constant, times q, which is unknown, divided by r, square root of 50 squared, which means 50 here, square root of 2 over 2, that's the cosine 45, equal to 10. Okay? The unknown here is a charge q. Huh? The unknown in this equation here is a charge q. So, you can now do some manipulation here to find the charge. Okay? If you do calculation correctly, okay, the charge will be 3.9 to the power minus 8 Coulomb, or 39 nanocoulomb. Okay? That's the answer to this question here. I hope this is a two-dimensional problem. Be careful, my son. And the net electric field is not 0, it's given to you, and it's given in with the direction, okay, which is minus j. So here, you take only the magnitude, and you don't worry about the minus sign. The minus sign with j, you don't worry about them. This is the magnitude, because I'm doing E magnitude here, okay? This is also magnitude. The magnitude of E along the y-axis is 10. You can read it from there, the net. And it's given also by this equation here, which are the two components of the electric field, the blue vectors. The two components are pointing downward here. So you don't need to put the minus sign because we are looking at the magnitude. So 2 is coming from the two components. Each one of them will contribute by this much, multiplied by 2, okay? And equal to 10, and you get the charge which is given by 39. So this charge, if you put it here, 39 nanocoulomb, you put it here, sure you produce an electric field of this much pointing downward. Of course, this is the magnitude here, okay? That's the magnitude. If he asks you about the sign of the charge, if you want to include the sign, it will be, the sign is what? Is negative, of course. So I discussed this point before. I discussed this point why it is negative, because the net electric field is downward. If for example, my electric field has a plus sign here, then the net will be upward. The 2x component will cancel, and the 2y component will add up upward, and the charge will have the same magnitude, but it will have a positive sign. Thank you. Okay, let's look at this third example about electric field due to point charges. Of course, we are using the principle which is called the superposition principle, where you have to add vectors add them as vectors. Okay. So at a certain point where you have if you have more than one charge, so you have to add, and you want the electric field at a certain point, you have to add those vectors. Vectorial sum of the vectors will be the net electric field. So 3-point charges are located at the corner of a square, as you can see, as shown in the figure here. This is D, D, and D, and D. So this is a square, two-dimensional problem. Find the value of Q again. If the electric field at the corner A is 0, okay, and he gave you the value of Q, Q is negative. You can see the 7 microcoulomb. All the charges are negative. These two charges are negative, and he's asking for the charge Q here, which makes the electric field here equal to 0. This is similar to the previous problem, but in the previous problem, the net electric field was not 0, but here it is 0. The idea is the same. So this is a kind of a repetition, but it will be good for you, my son, to practice on these ideas, okay? So let's draw the square. So this is Q is negative, and this is Q here. I don't know the charge Q, what is the sign of this charge. We'll have to find out later. And another charge here, Q, which is negative, and the point here, point A, where the electric field, the net electric field is 0, okay? So let's use what we call the superposition principle. The first thing we have to do is to draw the vectors E at this point here for Q1 and Q, for the two charges. I'm going to point, I call this one point number 1, 2, and 3 because we have to give them names, the electric field. You see here, the charge is negative, so from this point, the electric field will be in this direction. I'm going to call it E1. Charge negative, the electric field here will be in this direction. I'm going to call it E2, and I'm sure of one thing, that E1 and E2 are equal in magnitude because the charges are the same and the distances are the same. And the QE is KQ over R squared. So Q is the same and R is the same, so the electric field will be the same in magnitude, okay? Now, so definitely the sum of these two is not 0. So there will be an electric field due to this charge here. The sum of these two will be actually in this direction, if you agree with me. The resultant of this two will be, so to make electric field be 0 here, the charge here has to produce an electric field in the opposite direction. So I'm going to draw that electric field for that charge, Q, okay? It will be in this direction here. Because as I told you, I'm going to call it E3, as I told you, the net of these two charges, the net electric field will be in this direction, and I want the net field to be zeroed for the three charges, so E3 will be in this direction, so automatically I know the sign of this charge Q, it will be positive, okay? So the sign will be positive to have an electric field outward, radially outward. You can draw the distance like this, okay? Alright? So now we can start solving. Again, this is 45 degrees. I need this angle here, but it's not always 45. It's 45 because it is a square. This is D and D. Okay, so it is a square. So the diagonal make 45 degrees with one of the sides of the square. Now, he wants E net, so I have to work in 2 dimensions now. I have to work along the x-axis, but since I have only one unknown, I don't need the second equation along the y-axis. I will need only one equation. You will see this now clearly, okay? Of course, my E3, we need the component of E3 along the x-axis, and it is positive, you can see it. So that's the component here, okay? So E3, x I call it. So E3x, we have to cancel E1 to make the electric field at corner A to be 0. Eh? So this component, and this is the component of EY, of E3 along the Y. This is E3 along the Y. So E3 along the Y is going to cancel E2, and E3 along the X is going to cancel E1, and the net electric field at point A will be 0. Okay? So let's work along the X-axis, okay? So I have to write that E1 in magnitude should be equal to E3x. This is a one-dimensional problem. You don't have to worry too much, okay? It's a one-dimensional problem, but you need a component of this vector E3 along the x-axis. So the idea here is to find the direction of E3, the sign of Q, and then start working, okay? Once you get that correctly, start working, okay? So this is K, Q over, it's negative charge, but you take the magnitude, so don't worry about the minus sign of the charge, eh? Over what? Over the distance between the point and the charge, which is D and squared, okay? Equal K, Q, the unknown, in magnitude. I don't care if it is positive or negative charge, but it is positive here, but you take always the magnitude, over what? Over this distance squared, this is D squared of 2. So if I square it, I get 2D squared, okay? 2D squared, okay? Now, times the cosine of 45, which is square root of 2. Let me write down cosine 45 here, so that you know what I'm doing here. Cosine 45, and then K will cancel, D squared will cancel, and so you get Q equal Q over 2 square root of 2 over 2. So my charge Q I'm looking for, I know it is positive charge, its magnitude is will be 4q over square root of 2, or 2 square root of 2 times the charge q. We have to take the charge in magnitude, okay? It will be 7. We put here 7 microcoulomb times 2 square root of 2. If you do the calculation correctly, you get 19.8 microcoulomb. So the charge q will be 19.8 microcoulomb. That's the final answer, and the charge is, the sign of the charge is positive. It has to be positive, otherwise you can never have the electric field equal to 0 here. If the charge was negative, E3 will be pointing in this direction, and the electric field will not be 0 at that point. So you must have a charge which is the sign, a positive charge, to produce electric field E3 in this direction, and the components will cancel. If you go and work along the y-axis, believe me that my son, that you get the same answer, okay? The same answer, and try to do it, please, just to satisfy your curiosity. Try to do it and do along the y-axis. You do E1 equal E3. E2 equal E3y, and you solve the same way, and you get here the same answer. Thank you.